So one of the main ideas in everything things is that if we take a null geodesic and follow it past the focal point, it becomes non-prompt, meaning that a causal path could have reached the same destination sooner. So generally in this picture, time runs vertically, and non-prompt means there would have been another causal path that would have arrived to the past of the destination P. So a null geodesic is continued past a focal point. If P prime is a focal point, it implies that this geodesic gamma, viewed as a path from Q to P, becomes non-prompt. Now remember, the definition of focal points, well, a crude approximation to the definition of focal points is that the QP prime section of the geodesic can be deformed to a nearby null geodesic between the same 2 points. In that case, it's obvious that gamma from Q to P is non-prompt because the segment of gamma from Q to P prime could be replaced by gamma prime. Then gamma composed with gamma from P prime to P composed with gamma prime from Q to P prime is not a geodesic, so it's automatically not prompt. Rounding out the bend at P prime could enable you to do better and find another causal geodesic that would arrive to the past of P. The more subtle point, which was very important in the applications, it's enough if the geodesic gamma from Q to P prime can be deformed to first order. As a null geodesic. That's enough to ensure that continued past P prime, gamma will no longer be prompt. Now, when we got to this point, we first discussed the analogous point in the space-like case, and then in the time-like case. And in those cases, they're actually are rather simple pictures for proving the analogous statements. You find that displacing part of the geodesic from gamma to gamma prime has a cost which is of order epsilon cubed, where epsilon is the displacement. Epsilon is the magnitude of the displacement from gamma to gamma prime. I'm going through this a bit fast because we explained it in detail in both the space-like and time-like.
Professor Witten, I'm sorry. Do you mind sharing your iPad screen? I don't think we can see it.
You can't see it. You might have told me that a little bit earlier, if you don't mind.
Sorry.
Well, thank you for telling me now. Am I sharing the screen now? Yes, okay. Okay. I'm going to have to review everything I said, though. So the main idea in much of the course was that a null geodesic continued past the focal point, stops being prompt. So here's a null geodesic from Q to P, P prime is a focal point. If we could, gamma might be prompt up to P prime, but it's never prompt if continued past P. So I remind you the definition of prompt is that no other causal path from gamma could have arrived to the past of P. Now, if gamma can be deformed exactly to a nearby null geodesic gamma prime, then it's fairly obvious that gamma can't be prompt if continued past P prime, because we could replace gamma by this wiggly path, not a null geodesic and therefore not prompt. More subtle is that it's enough if gamma can be deformed just to first order as a null geodesic. In that case, that's enough that P prime is defined as a focal point and that gamma continued past P prime is not prompt, but the point is more subtle. When we got to this point in the space-like is wrong, in the Euclidean signature case, and also in the time-like case in Lorentz signature, we compared the cost from slightly shifting gamma to gamma prime by an amount epsilon to the gain from rounding out the band up here. The cost was of order cubed, the gain was of order epsilon squared. So for small epsilon, the gain dominates. And that was how we learned that to make a geodesic non-prompt, it was sufficient to have infinitesimal focusing. Now, I won't explain that in more detail now because we did it in more detail earlier for both Euclidean and time-like geodesics. But in the null case, the same estimates apply, but I find them less obvious. And therefore, today I want to give a more careful explanation where we eventually will use the Schrodinger equation rather than these pictures to explain that a focal point causes the geodesic to become non-prompt. So we're going to today do a much more precise analysis. And as the starting point, we're going to pick what are called Fermi normal coordinates along a geodesic. The intrinsic geometry of any null geodesic is the same as any other, and irrespective of the spacetime it's embedded in. The only intrinsic geometry is that the metric restricted to a null curve is 0. And for first order, the metric in the first order neighborhood of a null geodesic is also trivial. You have to go to second order before you see the curvature. So up to second order, near the geodesic, we may as well be in Minkowski space. In Fermi normal coordinates simply mean that the metric along the geodesic, let's say, is given by v equals xa equals 0. And the metric takes the Lorentz form. All this up to corrections of second order. That means corrections of order v squared, x squared, or vx. And that's true because until you see the Riemann tensor, you don't know that you're not simply in flat space. The Riemann tensor is second order. For any null curve, the metric on any null curve is simply 0. But in a first order neighborhood, you'd see the analog of the extrinsic curvature of a surface, which is the acceleration of the geodesic. A geodesic, by definition, is non-accelerating, so that vanishes. And only in second order, you see the Riemann tensor. So up to second order, the metric near a null geodesic can be put in a completely standard form. And for an F, so the geodesic is parametrized. Since it's at v equals x equals 0, it's parametrized by u. Well, it's parameterized by an affine parameter, which I'll call lambda to be more flexible. But in this particular case, the parameterization is just that u is lambda and v and x are 0. Now, because the metric vanishes up to second order, there are rather simple formulas for the Riemann tensor. And the one that we'll need is that along this geodesic gamma, in other words, at v equals x equals 0, the components RAU, BU of the Riemann tensor are just minus a half the second derivative of GUU with respect to XA and XB. So that's an easy calculation because if you take the usual messy formula for the Riemann tensor, everything here is 0 except that one term. Everything here is 0 because all metric components and their first derivatives vanish at u equals v equals 0. Now, so on this geodesic, let's pick 2 points, let's say Q and P, with lambda equals lambda naught and lambda equals lambda 1. And let's find a criterion. Our goal will be to find a criterion that will imply that gamma from Q to P is not prompt. So we'll literally try to find a more prompt curve that's close to this one. So our starting point is the curve v equals 0, xa equals 0. And we want to perturb it. And the most obvious idea would be to say that v should be epsilon times little v of lambda, and xa should be epsilon times little xa of lambda with some small epsilon. That actually is not the right thing to do because we want causality. We want to perturb under a condition of causality, which says that minus g mu nu dx mu d lambda, dx nu d lambda is non-negative. But in these starting points, we have du d lambda equals 1. In the unperturbed thing, we have du d lambda equals 1. And others, dx mu d lambda, well, dx d lambda equals dv d lambda equals 0. So as a result, if we make this simple-minded perturbation I've written there, to first order, you'll discover that the condition of causality is just dv d lambda non-negative. But dv d lambda being non-negative, u and v are like in Minkowski space t plus or minus z. So dv d lambda being non-negative is just forcing us to go into the future. So so any perturbation of this kind with dv d lambda equal to greater than 0 is less prompt than gamma. So the naive idea of perturbing everything in order epsilon isn't effective at testing whether our geodesic was prompt. The reason it wasn't is that the x's only enter the causality condition to second order, because the causality condition is quadratic in the transverse coordinates, and they're of order epsilon, so they appear in the equation in order epsilon squared. So the way we made the perturbation, in linear order, we only see v. There's a simple cure for this, which is that we should perturb v only in order epsilon squared. So we should have let v be epsilon squared times some function of lambda, and xa be epsilon times little xa of lambda. By the way, I'm not trying to perturb u. And the reason I'm not is that that would just be a reparameterization of lambda. That would just be a reparameterization of the same curve. So we're not interested in deformations that just reparameterize the same curve. That won't help make it more prompt. So we only have to perturb v and x. And as we've seen, the interesting case is to perturb v in order epsilon squared and x in order epsilon, because then they will both enter in the perturbation in the same order, epsilon squared. Now, if you consider this perturbation, you find that the causality condition is now interesting. Well, what is it going to be? Well, first of all, in order epsilon squared, what we're trying to do is to evaluate in order epsilon squared the causality condition for this perturbed path. In order epsilon squared will not get a term linear in V, which will be the same as it was before, except appearing in order epsilon squared. But we also get something from x. So x will now appear quadratically in epsilon. So we'll get a term which is just delta ij, or maybe I'll call it delta AB, dxa d lambda, dxb d lambda. And this comes from the Fermi normal coordinates. So in our Fermi normal coordinates, the transverse part of the metric was the Euclidean metric on the axis, Kronecker delta. So that shows up here and gives us Kronecker delta. But there's one more term in the equation, which is very important. And that comes from the fact that GUU isn't identically zero after the perturbation. So remember, the metric but then there's an order x squared term in the metric, also xv and v squared. We don't care about these xv and v squared because v is of order epsilon squared. But the x squared term is important. X is of order epsilon, so the x squared term in GUU will be important. And the causality condition one term in it is minus GUU times du d lambda squared. Well, that's just minus GUU because du d lambda is 1. And GUU vanished up to order x squared, but we have to take into account the x squared term in GUU. And as I told you before, the second derivative of GUU is a component of the Riemann tensor. I hope the -2 is correct. Yes, I think. So the upshot of that is that, well, at least as written in my notes, and I hope my factors are 2 correct, the causality condition comes out to be that dv d lambda minus the sum of the xa d lambda squared plus a half the sum of xa xb. As I'm writing, I'm worried if the 1/2 is correct, but anyway, we'll go for it anyway. We get this. So in our situation that we started with, we want V of lambda naught. So lambda equals lambda naught at Q and lambda 1 at P. We want V of lambda naught and XA of lambda naught to be 0, so that the perturbed path starts at Q. And then we want to ask if we arrive to the past of P. Well, a criterion for being able to arrive at the past of P is equivalent to V can be negative. So U increases this way, V increases this way in the picture. If you can arrive with the same value of U, so arrive means lambda equals lambda 1, so that U is what it is at P. So if you can arrive at the same value of U that P has, but with the negative value of V, that means you've entered to the past of the point P. So, sorry, we'll actually be more specific. We'll arrive. So you should ask what X is doing. So if you can have XA equals 0 at P, which means that lambda equals lambda 1, and V negative, then that definitely means that you've arrived at, you're entering lambda 1 to the past. So what's involved in V being negative? Well, this inequality gives a lower bound. V of lambda 1 is V of lambda naught, which we're taking to be 0, plus the integral from lambda naught to lambda 1, d lambda of dv d lambda. And we have a lower bound for dv d lambda. That's equal to or greater than the integral d lambda of dxa d lambda squared. There's an important minus sign. Minus a half r a u b u times x a x b. So what we learn is that our geodesic gamma from Q to P is non-prompt. If we can have, well, let's define the function of the right-hand side of this expression as J. Letting J of X be that function. So if we can have the upshot of the analysis is that if we can have J of X negative, while X vanishes at the endpoints of the intervals, then our lower bound on V at the endpoint is negative, and therefore V can be negative. This lower bound is the only condition on V because it did come from an evaluation of the causality condition. Well, this criterion might be familiar to you from elementary quantum mechanics, if I haven't confused you too much. At least I think if I remind you, you'll see that you know this criterion from quantum mechanics. I'm hearing another voice in the background.
Well, you look very switched there. You know, you have problems on it.
So think of XA as components of a column vector, or let's say a quantum wave function.
You get, I mean, I'm talking about that.
Is it an unrelated conversation we're hearing in the background? Does anyone know? So anyway, so take a quantum wave function and then define a Hamiltonian.
He's very sensitive. Don't tell him that Edward or he's the only one who's more sensitive than she is.
Are there any suggestions at all about the background noise we're hearing?
Yeah.
So our Hamiltonian is a standard Schrodinger operator with a matrix valued potential. The potential is our friend minus half RAUBU. Sorry. I didn't write this accurately enough, so sorry.
I'm disappointed you're disappointed. You're a real fan. You know what I mean.
Someone must be tech savvy enough to suggest what we might do about the background conversation.
For me, that
No? Sorry, I'm getting, I don't think anyone is muted, so you could be speaking up, which I wish you'd do, but I see people are answering in the chat. Okay. The suggestion is for people to mute themselves. I could mute everyone, which I don't like to do because I'd like to, you aren't able to unmute yourself once you're muted. You're not allowed to, you can't unmute yourselves. You're all muted. Okay. I thought I'd unmuted you earlier. Well, I could remember how to unmute you, but somehow the conversation has stopped. So for the moment, I'm just going to go on with the lecture. I hope I'll try to remember to look at the chat occasionally if there are questions. Okay. Okay. What has happened? So we found that if the right-hand side of this expression can be negative, then the curve becomes non-prompt. Well, what is this expression? Well, I introduced a quantum mechanical wave function psi whose components are the x's. And then I introduced a Hamiltonian that acts on it. And this function j is just the expectation value of h in the state psi. So j of x can be negative if and only if h has negative ground state energy. So now you can see what happens. Start with, first of all, a sufficiently small interval. Let P be just slightly. On a small interval, the ground state energy is going to be positive because since the kinetic energy dominates. As we move P to the future, the ground state energy goes monotonically down. That follows by the usual variational principle of the Schrodinger equation. You can use the ground state energy on one interval as a variational wave function on a bigger interval. So the ground state energy can only go down as you increase the interval. So if you ever get a zero mode, beyond that point, the ground state energy E0 is negative, strictly negative. And that implies non-prompt. So we've proved almost what we wanted to know. We've proved that if we continue past a point at which the Hamiltonian has a zero mode, gamma becomes non-prompt. This is almost what we wanted to prove. We'll need to do a little bit more work to show that. We want to show that this is equivalent to that this zero mode in this sense is equivalent to having a first order geodesic deformation. This isn't completely obvious because the question we asked was different. We asked if you could have a first order deformation that makes gamma, replaces gamma with a curve that's more prompt. And that's a slightly different question from asking if you can make a first order deformation that continues to obey the geodesic equation. We'll show that the two are equivalent, but that will require an argument. So modulo that argument, we've shown what we wanted, that if you continue past a focal point, that is a point where a zero mode appears, gamma becomes non-prompt. Before I give that argument, I want to explain an easy application to the ANAC though. But I think I really should try to remember how to unmute you all. Or, yeah. I'm asking all to unmute. Ah, I see. Now I'm allowing you to unmute yourselves. Yes. So if you have a question, please go ahead. I think you can ask a question now.
So in the Fermi coordinates, like they are valid for all u, like in this interval, it's and only perturbative in the like transverse directions?
I'm not sure what you mean by transverse. It's
Well, so the U and X V and X directions.
I'd call it longitudinal. The
Oh,
fixed normal
yeah, sorry.
coordinates are valid along U, but only up to second order in the what I'd call the transverse directions. To me,
Okay,
I
thanks.
parameterize the transverse directions. So Fermi normal coordinates might be more familiar for a point. When you learn general relativity, you must have learned that the metric at a point can be put in a standard form, and also its first derivative can be put in a standard form. And then the second derivative is proportional to the Riemann tensor.
Yeah.
Okay, the same is true along a geodesic, actually. The metric along a geodesic can be put in a standard form up to second order. And then the second derivatives give the Riemann tensor.
Okay, thanks.
The reason you can is that there's no intrinsic geometry. Until you see the Riemann tensor, you can't tell that you're not simply looking at a geodesic in flat space. Any other questions? Okay. I hope this argument was clear because it's really extremely simple. I'll just review it very briefly. Well, first point was that we learned that the perturbation that the right perturbation we made had to replace the normal, change the normal coordinate v in order epsilon squared because it appeared linearly in the equation. And the space like normal coordinates x, we deformed in order epsilon. Then we got a causality condition that's just proportional to dv d lambda times a quadratic expression in these spatial deformations. So the upshot is that to make v negative at the end point of the deformation, a certain quadratic function of x has to be negative. And that quadratic function, well, you've really seen such things in quantum mechanics when you discussed variational problems. The quadratic expression we interpreted as the excitation value of a Hamiltonian H in a state psi. Psi was just built as a column vector with all these spatial deformations as coordinates, as components. And H was whatever it had to be to make the statement true. But what H had to be is a Schrodinger-like operator, just the standard kinetic energy with the mass being 1/2 of a Schrodinger particle in d-2 dimensions, plus a matrix valued potential energy. And the matrix valued potential energy happened to be this thing. So we learned that when the ground state energy of the Hamiltonian is negative, then J can be negative. When and only when the ground state energy is negative, J can be negative. And that means that V of lambda can be negative. And the deformation is more prompt than the starting point. Now, so the key point then is to decide when the ground state energy is negative. Well, on a sufficiently small interval, it's never negative. As we I'm asking if I prefer we turn your videos on. It's entirely up to you. I'm happy to see you, but you don't have to turn them on. On a sufficiently small interval, with the boundary condition that the wave function vanishes at the endpoints, a Schrodinger operator always has a positive ground state energy. As we increase the interval, we can always use the ground state wave function on one interval as a variational wave function on a bigger interval. So the ground state energy only goes monotonically down, and it's not hard to prove that it goes strictly monotonically down. So if you ever get a zero mode, then beyond that point, the energy is strictly negative. So we get a criterion for when gamma becomes non-prompt. It becomes non-prompt when the Hamiltonian gets a zero mode. Beyond that, gamma is non-prompt. Now, that's almost what we wanted. What we wanted to know is that if the equation for a first order null, the question that we originally asked had to do with deformations that are required to obey the geodesic equation. And here we didn't impose the geodesic equation. So we'll make contact with the geodesic equation in a bit. But once we do that, what we have done will have proved what we wanted, which is that a null geodesic becomes non-prompt when continued past a focal point. Before going in that direction, though, I want to
All right,
make
Edward, just a very quick question. So what we're doing is like a particle in a box, because we also want x to be 0 at both ends.
yes, x is 0 at both ends because we're trying to deform the path in a way that, well, we want to deform the path in a way that starts at q, so that requires x to be 0. But then at p, if we can make x 0 there and v negative, then that means that we've arrived to the past. Now, since we are asking then for x to be 0 at both ends, it's, as you say, like a particle in a box. Whatever the potential is, no matter how negative it is, the energy will be positive on a sufficiently small interval. And again, no matter what the potential is, whether it's positive or negative, the energy will go strictly down as we lengthen the interval. So if we ever get a 0 mode, then past that, the energy will be strictly negative. And strictly negative means that our starting geodesic becomes non-prompt. Now, let's look for a useful criterion. To prove that the ground state energy is negative. And for this, we'll assume gamma is complete in both directions. That means that the affine parameter goes from -infinity to infinity. So in our study of Penrose's theorem, for instance, we learned something about geodesics that don't go forever, but here we'll assume this one does. And now we're going to use a variational principle. Suppose there is a constant c such that the integral of the potential, well, such that this integral is negative. Then I pick a variational wave function I can't literally use CA as a constant as a variational wave function because it's unnormalizable. For very small epsilon, I take a wave function which is a constant CA times this decaying Gaussian. And it will then be true for this wave function that the expectation value of the energy is negative on the whole line. It's negative because the kinetic energy will go to 0 as epsilon goes to 0. And the potential energy will go over to this integral, which we assumed was negative. So if exists such a CA, then the ground state energy is negative on the whole line. And hence, also on any sufficiently big piece. You see, if you take a very big piece of this geodesic, we couldn't use the Gaussian exactly as a trial wave function, but we could pick a trial wave function that's very slowly varying and has very low kinetic energy. The kinetic energy would be of order 1 over d squared, where d is the, let's say, lambda 1 minus lambda naught, the range of lambda over which we're solving the Schrodinger equation. And the potential energy will still be negative if it's negative on the whole interval. So what I've just told you is the following. Take the Schrodinger equation in one dimension. You could consider a case of if with many components, but you could just consider the ordinary Schrodinger equation for a single component guy. I've just told you something you might have learned in a course on elementary quantum mechanics. If the integral of the potential is negative, then the ground state energy is negative. That follows, well, in the case of a single component, you wouldn't have had to pick the constant c. That would just be 1. You would just use the trial wave function e to the minus epsilon x squared or whatever. And the same argument I just gave you would show that the ground state energy is negative. And you most likely have seen a version of that when you studied quantum mechanics. Maybe you only considered the case where v was negative definite, but in general, you only need the integral of v to be negative. So in the case of a multi-component Schrodinger equation, the only real difference is that we pick the constant c. And if the constant c gives, paired with the potential, gives us a negative value, then we make the same argument. So is there a c with 0 being bigger than CA, CB, PAB, which was minus half the integral d lambda CA, CB, RAU, AU, BU. Well, using Einstein's equations, if my half is correct, and I'm at the moment not sure it is, we can express this in terms of the stress tensor. Oh, sorry, we can't do that quite yet. So I skipped a step. Now we'd like to know if we can find a c which will make this right-hand side negative. So certainly some c makes it negative. Some c makes the right-hand side negative if the average is negative. So a sufficient condition for c to exist is that 0 is equal to greater than the average of the right-hand side. The average of the right-hand side is gotten by replacing CA, CB by delta AB over D minus 2. In that case, the condition is that 0 is equal to bigger than a multiple, which doesn't matter. Well, I replace delta AB, CAB with the multiple of delta AB, and I get just RUU on the right-hand side. And now is the right time to use the Einstein equations. So a sufficient condition for C to exist and therefore for a sufficiently large part of gamma to be non-prompt is that 0 is equal to or bigger than this integral, but that integral is just the Anik integral.
Some intervals postdoc and
Someone should mute, please. So a sufficient condition is that if the Anik integral, average energy condition, if the Anik integral for gamma is positive, then a sufficiently large piece of gamma is non-prompt. So I promised you on Thursday that we'd prove that. It was, knowing that was a step in showing that the Anik implies some results we proved Thursday. It implies topological censorship and the Galois-Wald theorem on causality in ADS-CFT. Now, we didn't need this Thursday, but it's okay if the integral d lambda of TUU is 0 and TUU is not identically 0. That actually implies that the ground state energy is negative. That's a statement about quantum mechanics that I didn't know, and it's harder to prove. I'm not going to prove it now. You can look at it in section 8 of my lecture notes. And there are more statements about criteria for that prove that sufficiently long pieces of null geodesics become non-prompt, which I also won't prove. I do want to stress that here it was very important that the geodesic was infinite in both directions. It's when, if you are working on the whole real line, then the integral of the potential being negative is enough to imply that the Schrodinger equation has a bound state. But that would not be true if you were working on a half line, for example, with Dirichlet boundary conditions. So there's no similar statement in the proof of Penrose's theorem, where we are looking at a geodesic that's only semi-infinite or potentially semi-infinite toward the future. It's when we're looking at a geodesic that's potentially infinite in both directions, as in these two problems, that the Anik is sufficient. Any questions?
We've demanded that the potential go to 0 at infinity, right?
Yes, implicitly, yes. I didn't make that explicit, but we assume PAB goes to 0 sufficiently fast at infinity.
This is also a fact that only holds in 1 and 2 dimensions, right?
No, this is a fact that holds in any dimension with, well, for example, in an asymptotically flat spacetime, the potential is given by the Riemann tensor, and the Riemann tensor vanishes rapidly at infinity.
No. An attractive potential possesses a bound state.
Yes, you're correct. That's right. Even 2 dimensions.
2
Well,
dimensions, yeah, it's fine. 3 is not though.
Well, it's definitely not true in 3 dimensions. Well, a negative definite potential certainly produces a bound state in 2 dimensions. But for the integrated version, I haven't thought carefully in 2 dimensions. Perhaps it's true. In 1 dimension, the integral of the potential being negative produces a bound state. And that's relatively obvious, and that's what I used here. As I said, there's a more subtle fact also true. If the potential isn't identically 0 and its integral is 0, that's still enough in 1 dimension to ensure that there's a bound state. Okay. The reason it was important that the potential vanishes at infinity is that I wasn't very, very precise in going from the ground state energy being negative on the whole interval, whole line, to a sufficiently big piece of the line. If you think that through carefully, you'll find that you need a condition on the potential vanishing sufficiently fast at infinity. It's a mild condition though, and for example, in most applications where you would have a geodesic that's infinite in both directions, it would be true. For example, it's certainly true in an asymptotically flat spacetime. Any other questions?
Edward, well, something that we're asking is if we define this integral over all lambda of R, A, U, B, U, let's call that some matrix. We just need that matrix to have some negative eigenvalues.
Right.
And so you're checking that the trace of the matrix is negative, for example, so that it clearly has to have negative eigenvalues.
Yeah.
But there are very simple criteria for checking whether a matrix is positive, for example. I mean, some statement about both linear as well as quadratic and higher conditions. All the upper adjusted determinants of the matrix have got to be positive, for example. Yes. Are any of these nonlinear statements interesting? You're only using a linear fact about this matrix.
I've never seen nonlinear statements used, but maybe that would be important. What I have seen used, though, there's an elaboration where you take into account the Weyl tensor. As well as the stress tensor. That actually is important. That was introduced by Hawking and Penrose in around 1968. I'm not planning to explain it, but you end up learning that it's extremely hard for a null geodesic to be prompt up to arbitrary values of the affine parameter in both directions. In fact, null geodesics that are completely prompt are very scarce. Null geodesics in Minkowski space, de Sitter space, anti-de Sitter space, and horizon generators for a Schwarzschild or a Kerr black hole are more or less the only examples. So a null geodesic is almost always becomes non-prompt if you follow it long enough. That's what one learns if one elaborates upon the sort of things I've told you, to include the Weyl tensor. Now, so remember, any more questions? So we started with this question. What we started with was a slightly different question from what we analyzed. We started with the question of a null geodesic deformation. But instead of looking at that, we looked at a completely general causal deformation. We found a criterion under which there was a causal deformation that was more prompt than we started with, but we didn't worry about the relation of that to having a null geodesic deformation. But it's usually true that the most prompt most prompt causal path is a null geodesic. So that would make you suspect that a zero mode of H is the same thing as a zero mode in the geodesic deformation problem. And I'm going to use the remaining time today to show that that's true. So we'll just remember that the geodesic equation And then that's the geodesic equation. Then we perturb it by replacing x mu by x mu plus epsilon times what I maybe call b mu. And here we want the deformation to be null. And the condition for null to first order and epsilon, well, we know all the condition for the original one to be null. So the condition that the deformation preserves the fact that it's null is this one. And we also want to satisfy the geodesic equation to first order. So that is that one second. Anyway, I've written the geodesic equation perturbed to first order. And it has uninteresting solutions. So it has uninteresting solutions because you could replace lambda by a lambda plus b with constants a and b. Those are just reparameterizations of the original solution, so we don't care about them. They correspond to b mu being a linear combination of dx d lambda and lambda times dx d lambda. So we want to look for zero modes, but we don't want to allow these uninteresting zero modes. So how do we look for geodesic deformations without allowing the uninteresting ones? Well, here's our geodesic that we start with, and here are the 2 points, Q and P. Let's say they're at lambda equals lambda naught and lambda equals lambda 1. We can avoid the uninteresting modes by saying that b of lambda naught equals b of lambda 1 equals 0. In other words, we solve the geodesic equation for geodesics that go between the given starting and final points at lambda naught and lambda 1, and where the geodesic interval remains the same after the deformation. The uninteresting modes would spoil that because they reparameterize lambda, and the points at which b vanishes would stop being lambda naught and lambda 1. So one thing that did was to remove the uninteresting modes. Now, if you combine the geodesic equation with x with this condition that made the deformation preserve the geodesic being null, you'll discover that there's a conservation law for the deformation. This is 0 because of our 2 conditions. If you differentiate here, the derivative could act on b, but that will give you something that vanishes because of the null condition, or could act on dx d lambda, and that will vanish because of the geodesic condition. So there's a conservation law. The g mu nu b mu dx nu d lambda is 0, is constant. But we want solutions where it's 0, because we want solutions where B vanishes at the endpoints. So this quantity vanishes at the endpoints, and being constant, it vanishes everywhere. So now we go back to Fermi normal coordinates.
Sorry to interrupt, Edward. Why isn't that conservation condition just the fact that the new curve is null?
Well, the new curve is null and the old one is the geodesic, right? If we act with d by d lambda on this, if the d by
Oh, sorry. The old curve wasn't necessarily null. Sorry about that. Thank you.
well, the new,
I mean, we want the new curve to have dx d lambda squared equals 0, but the old curve that we started with didn't have dx d lambda squared equals 0.
sorry. The old curve was a geodesic. We do use that. So there, we use two facts. The geodesic equation for the unperturbed curve and the fact that the perturbation is null.
Okay. Sorry.
I'm pretty sure that's all we use here. Then when we act with d by d lambda, it could act on B, and that would give us the condition that it was null. The deformation preserves the null condition. And we can act on dx d lambda, and that will give us the fact that the original geodesic was in fact a geodesic. Well, I hope that that's clear. Any other questions? So now we go back to our Fermi normal coordinates, where u is lambda for the original geodesic. U is lambda, and x and v are 0. And so we could write the perturbation in more detail, that v isn't going to be 0, but it'll be epsilon times some v. I'm just writing b in more detail adapted to these coordinates. U is going to be lambda plus epsilon times some new function, f of lambda. And xa will be epsilon times little xa of lambda. But the conservation law tells us that v is 0. This condition is exactly the condition that, since dx nu d lambda only has a term for x nu equals u, the only non-zero component of that is that v is 0. And then you find something nice, that the equations you get are, well, the first one is going to be familiar. And the second equation is now, before I look at that in detail, though, you should ask me why we're deforming u at all. In the previous discussion, we didn't deform u. The reason we didn't was that, well, the reason we're deforming u now is that we're insisting that lambda after the deformation is still an affine parameter, because I'm writing down the geodesic equation in affine form for x and v. So I'm assuming that after the perturbation, we have a geodesic with lambda as an affine parameter, and that means I can't assume that u is lambda. Previously, when we were considering an arbitrary causal deformation, the parameterization didn't mean anything. So previously, we just kept the parameterization lambda equals u when we made the deformation. But now that isn't in our hands. In fact, we have to satisfy this condition so that, well, we have to satisfy this pair of equations. which will mean that we have a geodesic deformation with lambda as an affine parameter? Well, the first one we've seen before. So a zero mode of H is a solution of the first equation. What about the second equation? Well, the second equation, you see, the second equation is linear in U, but it's got this inhomogeneous term. This is little u, the perturbation of capital U. It's got this inhomogeneous term that doesn't depend on little u. It's proportional to x. So the second equation always has a unique solution. Where u vanishes at the endpoints. By integration, you pick any solution. You write any solution of the equation. But then you can add a trivial solutions a plus b lambda. You can uniquely adjust the constants to make u vanish at two given points, lambda naught and lambda 1. So we've learned that the condition for a null geodesic deformation on an interval is the same as the condition for H to have a zero mode. So to tie things together, we've learned that P prime is a focal point if and only if H has a zero mode on the interval from Q to P prime. So that really completes what I was aiming to say today. So to summarize what we've learned, the main thing we did was to give a careful proof that a null geodesic past a focal point is non-prompt. I considered the proof by pictures to be pretty obvious in both the Euclidean case and the time-like case in Lorentz signature, but I considered the null case subtle enough that a careful proof was worthwhile. The proof I've given for the null case has analogs for the time-like case and also in Euclidean signature. Those analogs are much simpler because we don't have to distinguish V. There's no analog of V, there only are the normal coordinates X. So the discussion would have been quicker. If you look in math books on standard Riemannian geometry in Euclidean signature, you'll certainly find rather prominently the Euclidean version of what I've said today. And it's shorter, since, as I said, you don't have to worry about V. Anyway, I wanted to give a careful proof of this because it's such an important fact in everything we've said about general relativity and Lorentz signature, ranging from Penrose's theorem to the qualitative properties of black holes. Along the way, for extra credit, we proved that if the analog holds for gamma, so if gamma is complete in both directions, and the analog holds for gamma, then a sufficiently big piece of gamma is non-prompt. And the proof used nice facts about the Schrodinger equation that you basically knew from elementary quantum mechanics. And I think it's fun to have this application of things that we know from quantum mechanics, and I hope you enjoyed it as well. Thank you so much, and let me know if there are any more questions. Nima, or anyone?
And to this last point, here, if we only had that the integral of RUU or TUU was positive, let's say from some point on, not from minus infinity to infinity, but from 0 to some point, why can't we conclude that somewhere in that piece of gamma we would have non-promptness?
I don't believe it's true as a statement in quantum mechanics. So if you are on a semi,
I see. Sure.
if you're on a semi-infinite interval with a sufficiently short range and sufficiently weak potential,
Right.
I
Okay.
don't believe it produces a ground state
Right.
because the wave function is forced to vanish near the region where the potential is negative.
Right.
And you never win. You can make the wave function vanish very slowly in this direction, but that doesn't help because the potential is not negative there.
Right.
So if you want for Penrose's theorem to find out, okay, the ANAC is sufficient for, well, at least the examples we've given and probably other examples in general relativity, where you're looking at conditions that involve a null rate that goes on in both directions indefinitely, then the ANAC rather than a pointwise condition is sufficient. It's not going to be sufficient if you only have a semi-infinite geodesic, because the statement in ordinary quantum mechanics is not true. The closest analog for semi-infinite is what people call the QNAC rather than the ANAC. You have to replace the ANAC by the QNAC, which differs from the ANAC in that you consider entropy as well as an energy integral. I will be explaining some of the ingredients that go into the QNAC in the rest of the course, but we won't actually get a chance to discuss the QNAC. But the QNAC will lead to conditions somewhat like the classical Penrose theorem. That's what Raphael Busso likes to do, and others, of course. Any other questions? If there aren't more questions, then I think we can call it a day. I'm not sure about Thursday's lecture. I'm unfortunately home with COVID, which is the reason for this lecture being on Zoom. And we'll see if I'm able to give a lecture in person Thursday or if it has to be on Zoom on Thursday. If it is on Zoom, hopefully there will be fewer glitches. In any case, thank you very much for your attention. And see you next time, either in person or on Zoom, I hope.
Thanks, Edward. Take care.
Thank you.